First, we want to understand that we spoke about resting potential, and that was negative 70, and that's an important reference point for what we're going to speak about today. Okay, so negative 70 millivolts is where the neuron is at rest. Alrighty, and we're going to speak about the depolarization, the repolarization, and the hyperpolarization, which are all fluctuations in the membrane potential from that baseline of negative 70. Okay. Depolarization is going to be moving closer to the equilibrium potential for sodium, and we spoke about this on Friday. We said that sodium's equilibrium potential was what? What figure? Plus 60, so it's way up here, it's very positive. Potassium's equilibrium potential was negative 94, which is closer to the resting membrane potential because there were more potassium channels in the membrane. So the fluctuation of the membrane potential around this negative 70 are really the events that occur in an action potential. So let's talk about the channels first. Now we want to establish that what we've been speaking about so far with regards to establishing the resting membrane potential are really leak channels. And leak channels mean that they are not gated and there is no requirement to go through that channel. They're always open and they're throughout the entire length of the neuron. Okay, so those are the sodium and potassium channels that we've really been referring to so far. The ones that are always open, that are leaky, that do not need a ligand to open. Secondly, there are ligand-gated channels, and these open or close in response to some sort of ligand binding to them. We're going to see some of these when you look at the neurotransmitters that bind to certain channels and cause them to open. And these are located mostly in the dendrites and the cell body, the areas that receive the impulse from another neuron. So the dendrites and the cell body or the soma of that neuron. Okay. And again, ligand just means that it needs a chemical to bind to it, and then it will open. Then there are the voltage-gated channels. We're going to speak much more in depth about those today. They can open or close in response to a change in the membrane potential. So if the membrane potential becomes more positive, certain voltage-gated channels open up. If the membrane potential becomes more negative, certain other voltage-gated channels open up and others close. So voltage-gated channels are sensitive to the voltage or the change in membrane potential. And these are sodium channels and potassium channels. They're usually concentrated more in the axon, specifically the axon hillock. Okay, so by now we should be familiar with the structure of a neuron. The axon is that area just beneath or the neck of, so to speak, the neuron just under the cell body. And they usually have high concentration of these voltage-gated channels. Now, these are the channels that are responsible for the initiation of an action potential, these voltage-gated channels. Right? And lastly, there's the calcium channels below. These are more specific in the axon terminal, and these are responsible for exocytosis or the release of a neurotransmitter at the synapse. Okay, we're going to see these a lot throughout the rest of the semester. We'll see them in the muscle, in the muscular system, in the cardiovascular system. This is how one neuron sort of speaks to the other by releasing certain vesicles with neurotransmitters, and calcium channels are involved in that process. Okay, ion gating and axons. Now, it's important to understand that changes in the membrane potential are controlled through the presence or absence of different ion channels. So just like on Friday, we said that the membrane is more permeable to potassium. Simply means that the membrane has more potassium channels embedded in it. It's less permeable to sodium, means that the membrane has less sodium channels embedded in it. Okay, now there are two types of potassium channels in the membrane. There are not gated channels, which are always open. And these are sometimes called the leak channels or potassium leak channels. And then there are the voltage-gated channels, which are really involved in the action potential and are closed during the resting membrane potential. Okay, so I'll say that again. The voltage-gated potassium channels are involved more specifically with the generation of an action potential, and they are not open when the cell is at resting membrane potential. Sodium, on the other hand, only has one voltage-gated channel. These are closed at rest, and the membrane, as we said before, is less permeable to sodium at rest. Okay, so the influence of sodium on the resting membrane potential is really negligible. It's more about the sodium's permeability. Okay. Any questions so far? Any questions? Okay, so let's start talking about these different voltage-gated channels and how they change in their structure, their formation, as we depolarize the membrane, as we try to generate an action potential. So these channels open only when the membrane potential gets to -55. So we spoke about that number. That number represents threshold. All right, and threshold is sort of the minimum criteria for an event to occur. So an action potential will not occur unless we can depolarize this membrane to -55 millivolts. Remember, we're starting at -70. Alrighty? Now, at this time, when we get to -55, sodium will then rush into the cell due to its strong electrochemical gradient. And we said this before. Sodium has an electrochemical gradient where it wants to move from the outside into the cell. Again, because of the sodium-potassium pump, which is maintaining those concentration gradients. Now, as sodium rushes into the cell, the membrane potential will do what? What will the membrane potential start doing? Negative or positive? Sodium moving positive, right? Sodium is coming into the cell. It's a positively charged ion. As more sodium rushes in, the membrane potential starts moving upwards, right? Above -55. Okay. And what we have is certain channels that then become deactivated when we get to +30 millivolts. Okay. So really, the upstroke of an action potential or the depolarization phase of an action potential is really due to the movement of sodium through those voltage-gated sodium channels. And this rapidly depolarizes the membrane. Okay, now looking more specifically, more closely at a voltage-gated sodium channel, there are two gates on this channel. There's an activation gate and there's an inactivation gate. Now, let's just sort of describe these two gates, and then let's look at the events that actually occur. So an activation gate, first of all, is voltage dependent only. So it only looks at the change in the membrane potential. It is open at threshold and open during depolarization. Thirdly, this activation gate is a part of positive feedback, and what that means is that the more we have the activation gate open, the more sodium coming into the cell. The presence of more sodium creates a stronger gradient, which wants to sort of potentiate that loop of events. More sodium, more channels opening, more sodium, more channels opening, and that moves us further away from the set point, and hence it's a positive feedback loop. That is your activation gate. The inactivation gate is both time and voltage dependent. Okay, time and voltage dependent. I'll explain what that means in just a minute. It is going to be open during depolarization, and then it's going to also close during depolarization. So it's going to remain open for the length of repolarization, essentially. Okay. All right, let's look through these sequence of events here. So we have a cell.
Would you say again, it's open during like?
It's open during the phase or the time of repolarization. Okay. All right, that was the inactivation gate. Okay, so at rest, we have both the activation gate closed and the inactivation gate open. Okay, and again, these are the two gates on this sodium channel. The activation gate up here, the inactivation gate down here. The inactivation gate is sort of like a security, like a second gate that's sort of regulating the movement of sodium here. So we're at rest, and this gate is closed, but it has the capability of opening. And when it opens, the inactivation gate is also open. So the next step here is that this membrane becomes depolarized. Let's say we move from -70 here to -55. At -55, both the inactivation gate and the activation gate will then be open. What happens here? If both of these gates are open, then we have sodium rushing into the cell, okay? And that is what the upstroke or the upshoot of an action potential is. All of this sodium, positively charged, rushing into the cell, it's going to depolarize the membrane potential, and the inside of that cell gradually becomes more positive as it approaches this action potential, okay? So during the second phase here, we have the activation gate open and the inactivation gate open. Now, what's important to understand is that when depolarization occurs and this inactivation gate opens, there's also a second stimulus here. There's a delayed response, but the inactivation gate will then close after 1 millisecond. And that's why we say that the inactivation gate closes during depolarization. At the beginning of depolarization, this gate opens, but there's also a delayed response signal that is sent to close this gate after 1 millisecond. Okay, so that's this bit that may be a little bit confusing, where both opening and closing happen during depolarization, and that's because two signals are sent here. One is to open the channel, right? The second signal is after 1 millisecond to close that inactivation gate back. Okay, and then we get to repolarization here, which is where the inactivation gate is now closed and it's not possible to open it. The membrane must return to resting state, which would be the closing of the activation gate. And then we have sort of a loop happening here. All right, so I'll repeat this part again. The inactivation gate then closes. We cannot open this gate again until the membrane gets back to -70. And that is to ensure that we cannot fire another action potential until we get back to our resting membrane potential, the closing of this inactivation gate. Sort of like a security guard or an extra sort of fence to keep things secure.
Does that close at +30? Does that close at +30?
Closes at +30. Closes at +30 millivolts. And we're going to see that as we move on. So let's keep going here. So that was your sodium, your voltage gated sodium channel. There were 2 gates present on that one, and one was voltage dependent, that was your activation gate. The other was both voltage and time dependent, that was your inactivation gate. Potassium is different. The voltage gated potassium channels do not have separate gates, right? They're much simpler, and they are going to open at around +30 millivolts. So that's going to be the peak of that action potential, where we have the closing of the inactivation gate and the opening of these voltage-gated potassium channels. As these gates now open, potassium rushes into the cell, right? Potassium has a stronger force to rush into the cell because we're so far away from potassium's equilibrium potential. Remember that. Remember I said the further away we get from the equilibrium potential of an ion, the more force, right? The more magnitude that ion really wants to move according to its gradient. So because we're so positive now, potassium really wants to get into the cell now. Get out of the cell.
Oh, okay.
Yeah. Get out of the cell, again, so far from its own equilibrium potential. So potassium now rushes out. What does that do to the inside of the cell? We have positive ion rapidly leaving the cell. What does that do? Makes it more negative again. So we start approaching resting again. And in fact, we're going to go all the way down to potassium's equilibrium potential, and then we're going to slightly depolarize to rest. Okay, does everyone understand this? So potassium does not have separate gates. right? But it is voltage dependent, and at positive 30, these potassium channels open, potassium washes out of the cell, and so we rapidly repolarize the membrane by approaching potassium's equilibrium potential. Alrighty. So again, just to reiterate here, there's one gate, it's dependent on voltage and time, and this is a negative feedback loop, unlike what we saw with sodium. All right, we're moving closer to our set point, which is again, negative 70 millivolts. And we established this at the beginning of the semester. When we move further away from our set point, that's a positive feedback loop. When we get back to our set point, that's your negative feedback. Okay, so these voltage gated channels take us right back down to rest, which is negative 70 millivolts, and hence that's a negative feedback. Okay, so here what we see is that there are the voltage gated potassium channels. They are closed at rest, okay, and then they open during depolarization. So during depolarization, right, this is positive 30 millivolts here. These voltage gated potassium channels open, and then potassium washes out of the cell, and then we get back down to this refractory period where they're closed again. We cannot fire another action potential at this point.